Hi, boys and girls. In the last classes, we learned about the gates, the logic gates, and the properties of gates, especially the properties of NAND and NOR, that their non-associativity and universality. Now, in all these things, we have defined some circuits. Then we developed a truth table. Then we verified them with the cubes. But there is a reverse process also that is called synthesis of logic circuits. So you may be given a truth table, and then you have to look for which circuit is responsible for this truth table. So that is the synthesis of logic circuits. In this, you will learn quite a few things like sum of product expression, product of sum expression, the Karnoff maps, the logic reduction, and those things. So let me start with that presentation. So there are three sections in this speech. That is what you will learn, your learning outcomes. Then logic reduction by algebra. That is one method by logic reduction, and a summary of what you learned. So what you will learn in this session is that you will learn to design logic circuits for a given truth table. Some truth table is given to you, and you have to find out the logic circuit, sometimes a minimum expression, logic circuit for the given truth table. Now let us look one simple example. Let us look at this truth table. This is a three variable truth table. There are three inputs, A, B, C, and an output Y. So these are for 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these outputs are high for 0, 0, 1, 0, 1, 1, and 1, 0, 1. Now you have to find which circuit is producing this output. Given three inputs A, B, C, which circuit produces this output? I have to design that circuit. Now I have named these terms as MI, M0, M1 to M7 terms are there. Now you can see that for these combinations M1, M3 and M7, M5, I am getting Y equal to 1. Y is active high, or Y is true for the combinations M1, M3 and M5. Now, so you can easily say that Y is equal to M1 or M3 or M5, because for all these combinations it is a 1. Okay, for all these combinations. So when one of this is occurring, this output goes high. So this is an OR expression, M1 or M3 or M5. Okay, so what is this M1, M3? M1 is actually 0, 0, 1. So if that has to become 1, this should be A bar, B bar, C. This actually, M1 is actually the term 0, 0, 0. This should be a 1. So that means this 0 position should be complemented. A bar, B bar, and C. Now what is M3? M3 is 0, 1, 1. So this first term is a 0. So to make it a 1, I must make it a complement, A bar and B, C, so that this term will be, when it is 0, 1, 1, this term will be 1 and 1 and 1, so this M3 will be 1. And M5 is 1, 0, 1, okay, 5 is 1, 0, 1. So when it is 1, 0, 1, this is a term A, B bar, C. Now you have to see in this truth table that my A is the MSB and C is the LSB. I will use this term throughout, this convention throughout. So the last is 1, 0, 1. So this is for this term to become M5 to be 1, this should be A, B bar, C. So I write A, B bar, C. Now these are the three terms that go to 1 in this expression. Such an expression is called a sum of product expression, meaning that these are ultimately some products like A and B and C. Then this is another product A and B, C. This is another product A and B bar C. Now these things are ORed together. Okay, so this is a sum of product expression. Now I can either implement it as such, then in that case your circuit complexity may be high. In some case of programmatic implementation, also sometimes you implement that way. But if you are looking at gate level chips, MSI chips, then it is wise you go for some reduction, some logic reduction. So here this logic reduction is done by algebraic means. So here you can see that in the second and third term C is common. Okay, C is common in the second and third term. You know that these are distributive. So this is A bar, B bar, C, or C and A bar B, or A B bar. Now this A bar B or A B bar is nothing but A XOR B. So I can use an XOR gate here, A XOR B. And what is this C times A complement and B complement? A complement and B complement is nothing but A or B whole complement by De Morgan's law. A or B whole complement. So this is a NOR gate, this is an AND gate, this again an AND gate, then there is an exclusive OR, then an OR gate. So I can take out this C outside and make it A or B, C and in common, A or B complement, or A NOR B, or A exclusive OR B. Okay. So the terms in this SOP expression like M1, M3, M5, etc. are called min terms. Okay, some of product expressions are called min terms. Now the circuit looks like the C and what is it? C is common. The other terms are A NOR B and A XOR B. You have A NOR B, and this is A XOR B. The two are ORed. Okay. Then the whole thing that is ANDed with C. I will say that again. A is NORed with B. A NOR B. Okay. Then there is A XOR B. Okay. Then these two outputs are ORed. The inside expression, these two are ORed. Then it is ANDed with C. Now you have to note that when I connect these wires, I put these connection dots here. These are black dots. Okay, this is a good practice to know, because when we connect wires like this, it is not clear which is connected. This line is connected to A, meaning that this dot is there. This is connected to A. This line is connected to B. This line is connected to A. Even though this line is crossing over B, it is not connected to B because there is no dot here. And this connected to C. It is a good practice to put a dot, black dot, but you have to make sure that this bubble, this is different from this bubble. Okay, you have to put a black dot. You may verify this circuit in QX. I will run a simulation for you. I will run the simulation. This is the this is the equation. This actually this is a NOR, and this is an exclusive OR, that is ORed, logical ORed, then it is ANDed with C. Okay, now we have to run this simulation, and you have to, I am running this simulation for a truth table, so I have to verify the truth table. So these are connected to two sources each. This is for this is the LSB. This changes bit every time. So this is put for 1 nanosecond, 1 nanosecond. This this changes state in every 2 nanosecond. Okay, this changes states in every 4 nanosecond, so that I get an even pattern 0 0 0 0 1 1 1 0 0 applied to my circuits. Now I run this simulation. You can see the truth table here. This is 0 0 0 for you remember that it is for 1 no, this is not the circuit. Which are my circuits? Yeah, 1 3 5. Yes, M1 M3 M5. Yeah, this is a correct circuit. M1 M3 M5. So you can see that for 0 0 1 it's a 1, 0 1 1 that is 3, it is a 1, 1 0 1 or 5 it is a 1. All other values are zeros. So this circuit, so you can say synthesize the circuit from this truth table. Now when I run the simulation, you see that the circuit is working correctly. So this is the correct circuit for this truth table. So you can do similar exercise at home. Now we will do another simple example, that is a detection of a prime number. Say I have to detect prime numbers less than 8. So you know the less than 8 prime numbers are 1, 3, 5 and 7. Okay, 1, 3, 5 and 7. 0 and 1 are not primes. 0 and 1 are not primes. 2 is an even prime, 3 is a prime, 5 is a prime and 7 is a prime. Okay. So I have correspondingly I have these bits M0, M1 to M7 or min time 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1. Where are these values going to 1? Y becomes a 1 for 2, 3 and 5, 7. Okay, 2, 3, 5 and 7. Now I have to take these times corresponding to this, that is M2, M3, M5 and M7. So Y is equal to M2 or M3 or M5 or M7. M2 or M3 or M5 or M7, that is Y. Now what is this M2? This is the pattern 0, 1, 0. Okay, this is a pattern 0, 1, 0. So to make this a 1, 0 should be, the first 0 should be complemented. So it should be A complement, B and C complement, so that this becomes a 1. Now what is M3? It's just 0, 1, 1. So it is A bar BC, because this is a 0, 0 value, so it's a complement 1, 1. Okay, A bar BC. Okay, or this is a 5, that is 1, 0, 1. This M5 is 1, 0, 1, that is A B bar C, so that it becomes a 1. M7 is 1, 1, 1, so it is ABC. Okay, plus nothing, it ends here. This plus is redundant. So what I can do is, in the first two terms, if you look, this A bar B is a constant term, is a common term, not a constant term, it's a common term, I'm sorry. A bar B and C or C complement, okay, C or C complement, or here AC is a common term, so that it is B or AC and B or B complement. You know that X plus X complement is a 1. Okay, irrespective of the value of x. If x equal to 0, it is 1. If x equal to 1, it is 1. X plus x complement is always a 1. So it becomes A bar B or AC. A bar B or AC. Okay. Now I can implement this circuit in this way. This is A bar, that is ANDed with B. Okay. So one term has come. Then the second is AC. This is A is ANDed with C. This is goes into this OR gate, and this is my output Y. Okay. Now you can verify. So this will detect a prime number. If a 3-bit pattern is given at the input, it will detect the prime value at the output. Whenever a prime value comes, output goes high. Now let me run this simulation with QX. I will open. Yeah, there is this file prime.c. Now if you run this simulation, you can see that I am getting the same truth table, that is for 0 it's a 0, for 1 it's a 0 because both are not primes. For 2, that is 0, 1, 0, it's a 1. For 0, 1, 1, it is a 1. That is 3 is again a prime. 1, 0, 0 is not a prime. 1, 0, 1 is a prime, it is a 1. Then 1, 1, 0 is not a prime, that's a 0. 1, 1, 1 is 7 is a prime, so that's a 1. So this is how I detect a prime number. This is how I do the logic reduction for simple circuits. Now let us look at another simple case, another way of presenting the same thing. I have to design a logic circuit, so I have to synthesize a logic circuit with the SOP expression f of ABC. So those bits are named as ABC. This is a function of A, B and C. I assume that A is the MSB and C is the LSB. This is sigma M047. It means it is M0 or M4 or 7. So the summation here means logical ORing. So it is M0 sigma M047 means it is M0 or M4 or M7. Okay, so that expression F is nothing but what is M0, that is A bar, B bar, C bar, because it is 0 0 0. To make it a 1 I have to complement everything, A bar, B bar, C bar. Then there is M4, that is 1 0 0, that is A, B bar, C bar, or M7 is A, B, C. Okay, now this is my SOP, sum of product expression. Now I can have a minimization based on algebra. I can take out this B bar, C bar, which is a common term in the first two, that is B bar, C bar and A or A complement, or ABC. Okay, so it becomes a B bar and C bar or ABC. What is this B bar and C bar? This is a NOR gate, B or C complement. Otherwise I would need it, two inversions and then an ANDing. I can avoid this two inversions and ANDing by making it a NOR gate. This becomes a B or C complement or ABC. Now you can see this implementation in QX, whether you can see whether this truth table is correct, whether it is getting M0, M4 and M7. That is a func3, this. Okay, now this is the thing, this is what is this equation, that is B or C complement. This is B or C complement, this is a NOR gate. Okay, this is a NOR gate, that is B or C complement. This is a 3 input AND gate, ABC. So this is ORed here, so this Y should have the same truth table. So I run a simulation. You can see that it is M0, M4, this is 4, M4 and M7, they go, output becomes high during 0, that is M0, M4 and M7. Okay, so these are simple examples in which you do algebraic manipulation to get a minimal sum of product expression. Why do I minimize it? Because I can reduce the hardware. Especially when I am using MSI chips, I can reduce this hardware. Okay, so you learn to design, what you understood in this course is you learn to design logic circuits by algebraic reduction of SOP expression. Now this method becomes difficult, this algebraic manipulation may become difficult if these variables are more. Now I am putting a simple 3 input case, there may be 4 input or 5 input cases, so they are doing it with hand, with algebraic means is becomes very cumbersome. So what you do is, there is another method, a graphical method called developed by Karnoff, that's called Karnoff map, that we will discuss in the next class. I thank you all.